Here is the graph charting my main results. The video observation results are represented by the blue dots. The predicted position versus time graph without the drag force is represented by the green line, and the predicted position versus time graph with the drag force is represented by the yellow line. My system was a round-shaped stuffed animal. I stood in my dining room chair and dropped it from a height that was approximately 3 feet above the table. I made the origin of my axes at the center point of the stuffed animal while it was still in my hand. That way it falls in the negative y direction. The stuffed animal was about 5 inches or 0.127 meters long. Here are the results from my tracker video. I made sure to start it right before I let go of the stuffed animal and to stop the video right before it bounced, so right as it hit the table. As you can see, the graph is a pretty smooth line consistent with the stuffed animal's downward motion. My initial observation time is 0 seconds. The initial position on the y-axis is negative 0.003 meters. The initial velocity is 0 meters per second because it's starting from rest. The final observation time is 0.433 seconds. The final position is negative 0.871 meters. And the final velocity I calculated by taking the change in displacement over the change in time of the last 2 frames of the video, which gave me negative 4.818 meters per second. Now it's time to begin building the computational model. I begin by plugging in my initial conditions found in my tracker video into the model, the initial position, which is 0.003, and the initial velocity, which is 0, plugged in, and the initial time, which is 0. I calculated the approximate mass of the stuffed animal to be 0.02 kilograms. Before completing the computational model, we need to have an understanding of Newton's second law. These are the 2 main equations that will be used in the computational model. These are the other conditions that will pertain to our model. This model also includes the magnitude of the weight force and the magnitude of the drag force, since the net force isn't 0. So the magnitude of the weight force is 9.8 meters per second. The magnitude of the drag force was calculated by implementing this number into the code and continually running it until we got the final position that was found in the tracker video in our computational model. We have j hat set to 1 in the y-axis, which is choosing the positive y-axis as the up direction. Here's our calculation loop for the computational model. For the initial model without the weight force and the drag force, we simply have ball.vel equals ball.vel plus fnet times delta t divided by ball.m, which is the velocity equation from Newton's second law, and we also have the position equation from Newton's second law. For the initial graph, we would simply take out the drag force and only use the weight force for fnet. So we would just take out this line of code. This represents everything used in the last code, which includes both the magnitude of the weight force and the magnitude of the drag force. So in order to calculate the weight force, we have negative ball.m times g, which is the magnitude of the gravitational force, times j hat. For the drag force, we have negative b times ball.vel times the magnitude of ball.vel. Fnet represents the sum of all the forces acting on the object, so it is the gravitational force plus the drag force. When we run the code, we get these arrows showing the weight force and the drag force. So the weight force is pointing down, drag force is pointing up, and also the graph of our computational model, including both weight and drag force. After we've produced all of our models, we can finally graph each representation. The blue dots symbolize the tracker video, and as you can see, they stray from the lines of the computational model, the predicted position versus time, which could have been from human error of just not clicking in the right spots when analyzing the video. This green line underneath represents the initial computational model without the drag force, so only with the force of gravity. As you can see, it pulls the object a little bit further inward, so it makes the final position a little bit further down because we're not including the upward drag force on the model. The yellow line is the most accurate because it represents the drag force plus the weight force acting on the system. So what does it mean? Which models predict a terminal velocity? The model which represents the weight force and the drag force, which is the yellow line, best represents terminal velocity because it is the most accurate. What if the object was initially thrown downward? If the object was initially thrown downward, it would have a starting velocity that was not 0. If we test this out in our computational model and change the initial velocity to, say, -1, and we run it, we see that the graph is beginning to straighten out, so it's beginning to reach that terminal velocity, that constant velocity. Thank you for watching!